So this set of slides is about a concept called pointers, mainly. And it is traditionally a very hard concept for CSCI 40 students. It's one of the hardest ones. Okay, so pay some extra attention to these slides. Go back, study them hard. This is a cool little write-up. If you're interested in more information about pointers, there's also plenty in your book as well. But here's a good write-up by some people at Stanford for that. But yeah, we're going to learn about how memory works now. I'm going to try and make it seem less magical. We've talked a little bit about memory, but we need to go much further. Okay, so at the very least, this is my motivation for you. At the very least, by the end of these slides, you'll understand and laugh at this silly comic. But another reason to learn pointers is it helps you understand what's going on deep down inside of your computers as your programs are running. Once you get good at that knowledge, right, once you know how the computer is going to run your program at the lowest level, you can start optimizing for that, right? You can make your programs work very nicely and play very well with the hardware because you'll understand it a little bit better. Okay, so that's kind of the goal. To make you a better programmer, we should learn this because you'll understand how to make your programs faster, all right? And what they look like deep down, okay? So yeah, let's talk about first, what does memory actually look like? So we've got sticks of RAM inside of our computer. That's what memory is, right? Random access memory, or RAM. Another name for that. If you've built your own PC, you might know. But let's think about what does this mean? I've been drawing when we make a variable. I'm okay, X is a box in memory. We need to go a lot further than that now, all right? What does it actually look like? So some new ideas. All right, so your computer's memory, you can think about it at a lower level. It's ones and zeros in electricity form, but for computer science purposes, let's pretend that our memory, it's really just a big long table that maps addresses, things called addresses, which are big numbers, 64-bit numbers, to byte values, which are 8-bit numbers. Okay, so here's kind of the goal. Memory looks like this, really. All right, it's just a big long table that has addresses mapping to values at that address. So it's a very long table. Of course, I cannot draw all of it, but here's the start of it. The very first address is the 0 address. And you can store at the 0 address 1 byte's worth of information. You can store 42, 8 bits. All right? The next address is address 1 right after that. It's a big long table. It's like an array, essentially. It's an array of bytes. 43, you can store it at address 1, address 2, address 3, and there are lots and lots of addresses after that. Right? Depends on how much RAM is installed inside of the computer. You can have 33, 34, these addresses, and think of an address it's like you're about to write an email or you're sending a letter. It's like a physical place. It's the house of where that byte lives. An address is just a place where a certain byte lives. It's like its little mailbox, and you can send information through the postal service to that address, right? And you can look up what's there. So you can go hey, address 2, what do you got? 33. Hey, address 2, I have something new for you. Become 34, please. So it's just like an array where you can update the elements, the indices, maybe. Hey, address 3, become the largest possible byte value, 255. Something like that. So you can go send information to an address or look up what's there. And every time you make something in memory, it is taking up address space. All right? Every variable you make, everything you make in your program, a string even, it has some address associated with it where it begins, we say. Because a lot of things take up more than 1 byte, right? We know that integers take up, and strings take up multiple bytes, right? Integers take up 4 bytes total. And so there's always going to be a concept of where does this memory begin? It might take up multiple bytes starting at some address, okay? So that's the goal. And let's go further into that now, right? How do we store things that are longer than just 1 byte? How do we do it? Right? Because ints, for example, those are 4 bytes long. So when you say this in C++, what really happens? Let's do more than just this. It makes a box and it holds 42. Let's see what's going on. All right. So first of all, every single thing that you make, every piece of memory that you make in C++ has a starting address. Ints are 4 bytes long. They get stored in memory somehow. What they're going to do is they're going to take up 4 bytes, starting at some address. Let's say that X gets the address 16. That's just what the operating system gives it. So let's say that X is going to live at address 16 in memory, and it takes up 4 bytes. What that means is, here's the table of memory again. We'll shift downwards. Here's address 16. Ints are 4 bytes long. They can't just use address 16. They need addresses 16, 17, 18, and 19. So the 16 was just the start of it. Does that make sense? The 16 was just the start of it. And somehow in these 4 bytes, okay, that's how we're going to store 42, right? Somehow in this, we're going to take up, starting at address 16, the next 4 bytes, 16 through 19, and we're going to somehow place 42 within those. Okay, that's the goal. And so 16 is the starting address of x, where the int x starts. All right, does that make enough sense so far? That's kind of what's going to go down in memory when you make an int variable. It has a starting address, and it takes up more than just that address's worth of space. It takes up 4 addresses worth of space. And this is how we store everything. Strings included, just a bunch of chars, right, one after the other. Each character is a single byte, but you have multiple of them in order, all right? Doubles, for example, like everything becomes a number deep down, one way or another. Like doubles, they're 8 bytes long, and they're just a bunch of ones and zeros. So again, you can arrange them in 8 bytes worth of addresses, right? And then strings are made up of characters, and each character, bless you, is secretly a bunch of numbers, right? Just a bunch of ASCII valued things, and each character is a byte long. And so it's like an array of bytes with a starting address. All right, that's the goal. Okay, does that make enough sense still? That's what memory looks like. It's a big long table of addresses to values, and if you have things that are more than 1 byte long, you're going to take up a few bytes in order. Okay, a few addresses in order. All right, so to talk about things stored in memory, we need a new number system, actually. It's going to be a lot easier than talking about ones and zeros all day long, doing binary, because like that's a little too much typing. So instead of saying like, all right, here's the number, here's the byte in memory, these 8 bits, we're going to use a different number system called hexadecimal, all right? And C++ is going to print things by default, print addresses by default in this number system, so we need to learn it. It's called hex for short. It is not base 2, it's base 16. It's a power of 2. And so it's hexadecimal, and you can remember that, like, these are Greek roots, right? Hexa and desa, so 6 and 10, 16. So, all right. Like I said, right, decimal numbers, 10 digits, 0 through 9. Binary numbers, 2 digits, 0 and 1. 16, base 16, hexadecimal hex, we need 16 digits, right? And so we need to go past 9. So we start using letters, A, B, C, D, E, and F. So A in hexadecimal is a single digit that means 10. B is a single digit that means 11. C is 12, D is 13, E is 14, and F is 15. So you can go up to 15 in hexadecimal without needing a new base, without needing a new place, right? Count up to 15 before you need a second digit. But if you want to go one more, F, this is base 16 numbers, you want to add 1 to F, then suddenly you need to carry, right? It's going to be 1, 0, and that's the number 16 in hex, right? So that's the goal. And yeah, the terminal can't really print out subscripts very easily. It can't be like, this number is 3A and subscript 16. So what it's going to do when it prints out an address to you, it's going to say 0x at the start, and then it gives you a number. Okay, that's in hexadecimal. It just means pretend whatever I say after this, look at it like a hexadecimal number, please. All right, because you might get, right, 0x10, which looks a lot like 10, but no, it's saying, no, this is hex. This is the number 16, not 10. Okay? So yeah, let's learn how to break it down. So what is 3a in decimal? Can we break it down? It's going to be what? It's going to be a times, right? A times 16 to the 0 plus 3 times 16 to the 1. And remember, the a is just 10. A is one digit that means 10. So that's what? 3 times 16 plus 10. All right. And apparently that's 48 plus 10, so that's 58. Okay. That's what number it is in decimal. So that's hexadecimal. Some extra digits that are letters. Does that make sense? It's a little weird. But the reason we do this, the glorious reason that we have this, 16 is a power of 2, and it's very, very nice to talk about 8 bits or any number of bytes, because every 2 hex digits corresponds to 1 byte. So instead of writing out 8 digits, you can just write 2 digits and it corresponds, which is really nice. So like 00 is the smallest byte all the way to FF. That's 255. That's your largest byte. So I'd rather do this than write 8 digits. Right? 2 digits are much better. So yeah, that's kind of the goal. That's the reason. So like every 4 bits is a hex digit, essentially. That's how that works. Okay. So that's how addresses are going to be told back to us from C++. That's just a common thing, right? So, are we still good? New number system? Happy enough? All right, let's store a bunch of numbers. Let's draw some pictures, right? So let's say that we run this code, and let's think about what's really going on under the hood in the table that is memory. Okay, is there a question first? Okay. 10 base 16. This is the last digit, so we need a new place. Just like when you add 9 plus 1, we run out of digits in decimal land. We have to add a new place. 10 decimal is 10. And so, same idea. We have to carry the 1. 10. Yeah. Try it. Try it a couple times. Try it in binary too. I think it'll help. Yeah. It was a little weird though. I agree. But yeah, let's store some integers and let's think about what these lines really mean now. All right. So we know that they're going to make boxes in memory, but what else is true about them? Like, okay, all right. I used to draw it like this, right? X is going to hold 42. I'm going to make a variable called y that holds 43. And then int z equals y. Notice also that this is making a brand new box every time you say the type. Right? It makes a brand new box in memory. It's the third place in memory that holds the same value as y, though, so 43. All right. So they make boxes in memory, but what else can we glean from this? They're all going to be separate boxes, right? Which means they're separate places in memory, which means they all have separate starting addresses. I'll just make some examples of, like maybe X starts at address 4. If they're going in order, Y cannot start until address 8, because they take up 4 bytes apiece. And then Z can go at 12, maybe. So they're all separate boxes, which means they all have different memory addresses. And actually, that's the same idea, isn't it? That's just saying the same thing twice in a different way. Okay. So those two ideas correspond, which is interesting and cool. All right. So what does it look like in memory? Address, value. This is the big long table. Here, let me make it a little bit more normal looking. So, all right. Starting in address 4, we have X, which is going to be held in 4 bytes, 4 addresses. So 4, 5, 6, and 7, that's where X is going to live. Somehow we're stored in 42, all right? And X starts there, okay? And then at address 8, taking up addresses all the way to 11, we're storing Y, right? Which is 43. That's where Y begins. And then what, 12, 13, 14, and 15. If we pretend that Z is starting in address 12 for real, then that's where Z will be held, and we're somehow storing 43 again in those 4 bytes. And there's plenty more addresses right after that, all right? So that's where Z begins, all right? And so, actually, the second you compile your program, what the CPU is looking for is, it's like, I know that my variable that I want to look at right now is an address 4. I know that this next variable is an address 8. I know that this is an address 12. There are no variable names inside of a computer, right? Inside of the CPU as it's running. That's just for us humans, right? Computers, they use addresses. So this has an even more stronger correspondence, okay? This is just the computer's name for our X variable. That's its address. That's where it begins. That's all it needs to know. Where does it start? Go work with an int there. Okay. Any questions about that? So that's what's going to look like in memory. Yeah. Yeah, we're getting there. Finally, I'm going to slowly teach you what that means. Yeah, we're getting that's pointers. Very good. That's exactly right. These slides will help that make sense. But all right, I have a question for you now. It should be a little bit of a review, but just let's make sure we're awake. Do attendance. I'll stop attendance after this, but let's break out the by clicker page, please, and say hello to your neighbors. Convince them that you're right. But let's say we're making a silly program to model that it's somebody's birthday, so their age is 19 now. I'll print it out. We call birthday on age, and it's meant to do this, to increment stuff, right? Print it out, we call it. It does that thing, and we print out age again. What will happen? Do you remember? All right. Pretend that everything above is as it should be, like include IOStream and all that. What will you see? All right. See if you can figure it out. I'll give you a couple minutes to convince your neighbors. Technically, this should be a review. There's nothing new about this particular question. Yeah, I think I might be doing in this whatever it's called. Set of slides. Alright. Let me look at this real quick and then we'll look at your answers. Alright. Let's see. Do you remember? 5, 4, I'll give you a couple more seconds to input your response. Alright, let's see what we're thinking. Oh man, look at us. With a slight majority, we're thinking B. I think we forgot about the references slides, didn't we? Well, it's good that I'm giving you these questions, though. It's a good review. So I promise to stop that as well. So the answer is going to be, drumroll please, it's going to be A. It's going to be A. It's not going to be B. Because what's going to happen is age is being passed into int A. This is a normal int variable. It's being copied. A is increasing, but that's doing nothing to age. Does that make sense? If you wanted to change age, this should have been a reference A. That's one way we could have done it. Right? There's going to be a new way that we could have done it that I'll show you in these slides, though, with pointers. But yeah, under the hood, here's the stack, right? We can think about this in terms of addresses now, which is beautiful. So main, which has an age variable set to 19, right? Maybe that lives at address 100. We're calling birthday, right, which has its own A variable, and it's just a normal int, so it's local to that birthday function, all right? So A is getting past age, the same value. It's getting past 19. It's getting to C19, but it's living at a different address. It's a different place in memory. It's a different variable. You see that? So addresses help us learn as well and understand the problem. So A is being increased, of course. A equals A plus 1, sure. But then that function immediately returns and you did nothing with A, right? We're back in main now. And so sad, age has not changed, right? It's like you never had a birthday. Does that make sense? Remember the problem now? So yeah, you can think about it in terms of addresses as well, which is exciting. Oops, I want to delete that stray mark. I guess I can't. Never mind. But yeah, one way you could have solved this was to use a reference, right? So we know that answer. But references are secretly actually using this new concept called pointers. It's doing it for you. It's making your life much easier because pointers are difficult. But I'm going to teach you what's really going on. So I technically lied when I said that pointers don't create any, or references don't create any memory of their own. They're secretly going to use pointers, but it's a constant amount of extra memory, so it doesn't really matter. You'll learn that in 41. Okay? So let's talk about it. So let's talk about what a pointer is. That's the main topic of these slides now. I had to do all of that to get to here. All right? So a pointer is just a special type. Question first? That's a great question. What's the best way to explain that? So, I don't know. We could have, let me show you. Do I have a program yet? I don't. Let's go to, let's look at a program from last time, Vim namespaces. That's CPP. We call C++ a high-level language because it looks like English. We're saying these are normal English words, yeah. Namespace, 42. So we're telling the computer to do stuff at a high level, we say, all right? There's a lower level. There's the CPU level. If I say G++-S namespaces.cpp, it will create what's called assembly code, namespaces.s. You don't have to ever remember this. But these are CPU instructions that are hard to understand. There's some English words, but you see how it's spelling things out, and it's like it looks a little jumbled and weird. This is a lower level program. It's closer to the CPU. It's talking more closely with the hardware. Does that make sense? Yeah. That's what I mean by lower level. Okay. Yeah. Yeah, it's like, are you talking to the actual electronics of the CPU, or are you like talking English? Like that's the gradient, high level versus low level. That's a great question, though. Yeah, does that make a little bit of sense? Yeah, that's the goal there. So yeah, you'll get to learn assembly in 45. Yeah, so hold out for that. It's very exciting. All right. So yeah, a pointer. A pointer is just a special variable that holds an address of somebody else. All right, that's the goal. A pointer is just a special kind of variable. It's another box in memory, but what it holds is special. It holds the address of somebody, the address of another variable. All right. So when it holds somebody's address, we say that it points to that variable. That's why it's called a pointer. All right. So this is what it looks like to declare a pointer. It's just a normal variable, so it has a normal name, but it looks like this. You say the name of a type, whatever it's about to point to, like int, it's about to point to an int. So you say int, and then you say star. All right. So like int star, give it a name. All right. Or double star, give it a name if you want to hold a double address. All right. You can put this star anywhere. I'm going to put it next to the type. Like it just like references, the ampersand could have gone anywhere. The star can go anywhere. So white space doesn't matter as long as it's between the type and the variable name. And pointers, they're very, like you need that type as well. It's not just like I am making a pointer right now. I'm making a pointer that will hold an int address. That's special, all right? So here's an example, int star p. This makes p as a pointer, right? It's just a box in memory that's capable of holding integer addresses. All right? That's how you read that. You kind of read it backwards. P is a pointer to an int. Okay? And by default, just like any other variable, it has its own address, like it's a place in memory where that P lives, but it's capable of holding other people's addresses, not its own. And it currently holds garbage, right? If you're not ready, if you don't have an int ready to have P point to it and have it hold its address, you can give it, bless you, you can give it a very nice default value called the null pointer. So null, like nothingness, the void, that is just a special address that's unused. It's actually the zero address. So null pointer is shorthand for just like the zero address. It's a special address that nobody ever gets access to. So like actually you can't ever put anything at the zero address. Okay? If you are a program, at least. If you're the operating system, you can do whatever you want. But if you're a program, you can never use the zero address. That's the special unused address that everybody's just agreed to never touch. All right? And so that's a good default value if you're not ready to have something yet. All right? So that's a pointer. It has a place in memory. It's capable of holding integer addresses if it's an int star. It's capable of holding the address of some other int variable. All right? And so let's slowly but surely draw some pictures and and then write some code too. Okay? So here's an idea, right? So let's make an int and a pointer to an int, and we'll draw pictures, right? So if I say int x equals 5, here's x. It's got an address, right? I'll use hexadecimal for fun this time. And it's holding 5. And if I say int star p, that again makes a box in memory. It's just another variable, but what it holds is special, right? It has its own memory address, and p is capable of holding, it's holding garbage right now, it could hold the address of an int. We're eventually going to give it x's address. So what I want to put in here, eventually, is 100, okay? And that's the goal, because that's the address of x. That's the address of an int. It's capable of holding that, okay? So here's how you do it. Here's how you set p to hold the address of x. Here's the syntax. It's the ampersand again. I'm so sorry. So if you use the ampersand outside of a type, because you know inside of a type it means reference. If you use it outside of a type, just in an expression, it's called the address of operator, and it takes something after it. All right? So you read it as the address of something else, and it's going to give you back, kind of returns, the address of like a variable name that appears after it, for example. This is how you do this setting. You say p become the address of x, ampersand x. All right? This will compute the address of x. That's how you read it. Address, because it's the address of operator. All right? So I'm sorry that the ampersand already means something else, but here's another thing that it means. It means the address of when you use it like that. All right? And that will set p to hold 100. And so now it knows where x lives, and we're going to draw it like that. We're going to draw an arrow because it knows where x lives. It knows its address. It can get to it. It's pointing to it. Right? That's how we're going to draw that picture. Okay? So that's the first setup. Let's see, what do I want to do next? there a question first? Yeah. If I printed P right now? That's a great question. I'm about to get there. That's exactly where I wanted to go next. So I'm gonna show you in just a second. Let's do that now, actually. Let's do, here. Let's go to code, and we're gonna print P and print X and all those fun things. Let's see here. Pointers.cpp. So let's say int x equals 5. We did that one already, right? Let's go back to this code. And let's just do int star p normally, like garbage, int star p, right? So p is a pointer to an int. It can hold, it doesn't yet, it can hold addresses of ints. And right now it's garbage. And so to answer your question, if I print p just by itself, that's going to go inside of the box that is called p and give me back whatever it was holding. It's going to print an address. So that's how you just get the address that it's holding, just by saying print p itself. There's a way to follow the pointer that we'll get to in just a second. But if I just print p, I'm going to print garbage right now, and I'm just proving to you that's going to print that garbage as hexadecimal. So there's the garbage value that was just by default in p. Something weird. It's different every time because the program's getting loaded into different places every time. Yeah. Yeah, I mean, yeah, just like if you print x, it's printing 5. It's not printing its address or anything. Just like p is another box. When you say its name, it's giving you the value in that box. And if we're not ready yet, we can say p equals null pointer, which is a nice unused address. Null pointer is a special unused address. And if we print that, that's going to be the 0 address that we just all decided to never use. So that's better now. All right, but I do have an x. I can set p to hold the address of x. P equals address of x. All right, I can do that, and let's print nat. Now, if I print p, that's going to print out the address in memory of the x variable, finally, like a real thing that's belonging to our program, a real address that we care about. So apparently, when I ran the program, that's the address of x, because I printed whatever was in p. Okay? If I rerun it, it's going to get loaded in memory in a different place, but x is living in that address for this run of the program. Does that make sense? That's the secret. All right? So yeah, if you just say p by itself, it's just going to go just like saying x is going in the box and giving you what's there. So it's going to print the value, just the address that it's holding. Okay. Here's how you actually use the pointer, though. Like if p is pointing to x, there should be a way to, through p, like follow this, right, and get to the x somehow. Wouldn't that be nice? Dun, dun, dun. I kind of want you to discover it, all right? So it's this star operator, all right? I think I kind of gave away the answer, but let's just prove to ourselves that we understand it. So it's the star operator called, again, we know what star means. It does multiplication usually, but if you use star outside of a type, and like inside of a type, it means pointer. If you use it outside of a type, it's going to follow a pointer, and it's called the dereference operator. So it follows the pointer. And so what do you think this should print now? See out star p. I think I kind of gave it away, but here, I'll give you a few seconds to imagine what should happen here. If I say star p right now, the memory looks like this. P is pointing x. X is address 100. P is holding 100, but P's address is 104. What should star p do? What do we think? Knowing this, we should already be on the page, right? But like, give me your best guess. Give you another 10 seconds or so. What should it mean to follow a pointer? Either we're confused or we're not on the page anymore. But yeah, either B or C we're thinking. So I'll show you the answer in just a second. Let's do it. Let me show it to you now. See out star p. So this is called the dereference operator. All right? The dereference operator, what should it do? Whatever should it do? Print. We're thinking that it might print 5 or it might print 100. We're not sure. It prints the 5. It follows the pointer, and it looks at the value in that box, the box that it's pointing to. So it's going to follow it and get the 5 out, and so the answer should be B. All right, question? Exactly. So yeah, that we have other ways of doing these two ones already. So star needs to be the new thing. So we have a way of printing 104 right now, right? Don't we? Because that's, I mean, it's a little weird to think about, but it's the address of P, right? The address of P is 104. So that's one way to print that out. And then what's the way to print out 100? Well, you actually have some options. You can print out the address of X, because that's 100, or you can just print out P. If you just say P by itself, that prints out the thing that it's holding, which is that address. That's another way to print 100. Okay. So star P is like if you have a pointer to something, you're able to follow that arrow and look at the value at the address that it's pointing to. Okay, that's the goal. And so in essence, the second you have a pointer, saying star P is equivalent to just saying X. Does that make sense? It's an alias, and so secretly, this is what references are doing for you. All right, setting up pointers, following them for you. That's the secret. All right. So let's see what else. And yeah, that gives you a new way to access somebody else's memory, right? Dereferencing a pointer gets you the value of the thing it's pointing to, or the pointee. Yeah, that's giving you the thing in that box, the thing in the box that it's pointing to. So if X lives at address 100, and it holds 5, and then P lives at address 104, but we don't really care about that, and it holds the address of X, so it's pointing to X like that, you can use that dereference to both get the value like we were doing with the cout, and you can also use it to modify, right? Because star P, for all intents and purposes, if it's pointing to X, if you say star P, it's X. It's the same. So star P equals 6. That's like, all right, what am I about to set? Star P, what is that? Well, P is pointing to address 100, so let's go to address 100, and now I'm setting this box to 6. See that? That's what it will do. So this will become 6. And then star P equals star P plus 1. All right, let's go. Star P plus 1. Star P is 6. Plus 1 is 7. Store that where? This place. So that should make 7 there. Question?
Can you name a counter variable the same thing with an asterisk before it? Like so that you can track what
Say that again. Give me an example with this.
like,
what should I name it here?
X, you just put asterisk X.
Asterisk is an operator. It's a special character. It can't be part of a name of something.
Okay.
Is that what you mean?
So it has to be a different name.
Has to be a different name.
But I guess you could just put pointer variable.
Yeah, it can be like X pointer or something. I don't know. You call it whatever you want, but it has to follow the same rules as a normal variable. It's just another variable.
So is this just like another way to do like traditional variable assigning and like grabbing the variable? Is like it just like surpasses like class variables? Like is that what it's supposed to do?
It just gives you more control over memory is my answer for now. There's some really cool things that you can do with pointers that I'll show you later that just don't exist with anything else.
And it just kind of saw as like an alternative to like regular variable. Like you could just, in my mind, take the value of the variable without pointing to it. But
Yeah, exactly. So essentially what I've shown you so far is this is an equivalent to references, to using references right now. It's a little bit extra work though. And so I'll show you the power of it later. But think of it right now as it's an equivalent thing to references. So essentially, star P is an alias for just X. So like this line is saying X equals 6, essentially. You could have done one or the other. And just like this line, like star P is equivalent to X, it's an alias. This is essentially doing X equals X plus 1. Do you all see that? So yeah, that's the goal. And that's the idea. So yeah, let me show that to you in code. And then we'll fix up one of the previous examples. So star P equals star P plus 1. Please don't talk while I'm talking. That's a lot. It's hard to hear. Think. All right, let's do cout X and cout star P. All right. So this should make it, right? What was X holding before? It's holding 5. So this is going into that place in memory, making it 1 bigger, and storing it right back at that same spot. So like X and star P, those are equivalent things to say at that point in time, okay? So they're both holding 6 right now. You see that? That's very nice. That's super duper nice. All right. So yeah, any questions about that before I show you, like, obviously, like if you know where X is, just say X. That's a little silly to do it this way. The power, again, like reference, is it comes when you're passing values to functions. All right, that's gonna solve this birthday example in a different way. Okay, that's the goal. All right, so here is one way to fix the birthday problem. Instead of using references, like you know the way to do that, instead of using references, you could have done, you could put the star over here if you want, just doing that for fun. You can use pointers. So, all right, how can we fix it like this? Age is 19, print it out, print 19, and then make it birthday take a pointer to an int. A pointer to an int, somebody else's memory address, all right? So we can pass along the address of age, see that? Into A. Isn't that nice? And so A is going to hold the address 100. So it's pointing across function boundaries to somebody else's memory. Isn't that glorious? And then we finally have the ability to follow that pointer and mess with it. Star A plus 1, store that back into star A. Well, that's just age. It's an alias for it, okay? That is what's going to happen there, and that's going to make it 20, okay? That's essentially what's happening when you use references, all right? That's the magic of it all. Does that make sense? That's another way to do it now. All right, so that's called call by address is the name for that. Just like call by reference was the other one. Let me show you that in code. Let's do call by address dot cpp. All right, so let's do exactly this program if I can keep most of it. Famous last words though. Let's see. Will it print properly? Will it paste properly? Of course not. But that's okay. I know the secret. All right, we have a special weird space variable. Space. That silly space character with a normal space everywhere. There. So this is call by pointer, and normally I'm going to put the star next to the type like this, but obviously it could have gone anywhere, just like references. Oops. Call by address. Dun, dun, dun. All right. So yeah, it's going to make it 20. We're passing the address into the int pointer. We're messing with it there, and that's messing with main's memory. Isn't that glorious? Questions about that? So yeah. It might seem like, why don't we just use references? But like now you know the secret, right? I had to tell you why the references are doing it the way they're doing it. Now you know. Is that a question? No. Cool. All right. So the second you have pointers, you can do weird looking stuff. Right? Here's a fun idea. So here's a diagram with pointers. We call it a pointer diagram. So if x is the original variable, and I have a bunch of pointers like this, pointers to pointers even, what are all the different ways to change x? Can you see it? Can you see all the ways? So, all right. If I wanted to change x to something different, I could have said x equals 6, like that's a normal way. I have a pointer, right? P and Q are two different pointers holding the address of x. So I can use either of those, right? I can say star P equals 6. Couldn't I? What else? What else? Star Q equals 6, right? Do we all see that would work as well? What about this one? How could we use R to change x? Do you kind of see what might need to happen? Yeah. Double star, good. Because if you do one star on R is holding the address of Q. Just saying star R, that's equivalent to saying Q, right? Just like imagine this said Q instead. And now we're doing the same thing, just add another star. All right, so add another star. You don't need any parentheses or anything. Just star R, because one star gets you here, and another star to dereference 100 to get to here. See that? That's a little weird. Star R equals 6, and that will give you another change. All of those will change this to 6. Okay? That's very interesting, isn't it? And we also now have to worry about the types. Like, how was R declared as well? So if I give you this as well, do you think you could figure out, like, could you set up memory like this? What would the types of P, Q, and R need to be? Like, X is an int. Let's pretend. And I'll do this in code in just a second, but let's think about it. Here's some new notation, by the way. You'll see this one day. But if you say the name of a variable and then a colon, what you put next is meant to mean the type of that thing. So X's type is int. Some programming languages work like this. This is like a formal thing. So X has type int. What are P's and Q's type? Right? What's the type of P? And star. Very good. So yeah, I'll use that kind of notation. Q is also an int star, right? And then, okay, let's think about what R's type should be now. So R wants to hold the address of an int star, yes? R would like to hold the address of Q, which is itself an int star. And so I need to figure out what the type of ampersand Q will give back to me, essentially, right? Because how did I set up P and Q themselves? Like, how did I say P equals what? Q equals what to have it hold 100? I said P equals ampersand X, right? And so what's the type of ampersand X? If X is an int, the address of X is going to be an int star. Does that make sense? Int star is a pointer to an int. That's what we're shoving into P, so that's got to be the same type, right? So the second you add an ampersand, you add a star to the type. That's the trick, all right? So the address of X, it's an int pointer. That's what it's doing. So that means the address of Q, if Q is the address of an int, if Q is an int star, the address of Q, what's the type that will give back? It's got to be, an int star, star. Just like this was that. You tacked a star at the end. Q is that. You got to tack a star at the end if you want to hold its address. That's got to be the new type. That's int double star. Does that make sense? That's the trick. So that's how you would declare these things. Like it's normal int X. It's int star, single star, right? It's holding the address of an int. Int star P, int star Q. That's a weird looking star. Let me fix that. And then it's going to be int double star R. All right, and here's how you think of it. Again, R is going to hold the address as a pointer to an int star because it's going to hold Q's address. See that? That's how it's got to work. That's the secret right there. So you can break it down like that if you'd like. So all right, what would that mean? Like if I made an X here and had it hold the address of R even? Like what would X's type have to be? Int what? Z. How many stars? 3 stars. Well, if R is an int star star, and I want to hold its address somewhere, it's got to be an int star star star. Okay? Oops. And that's how Z must have been declared. Interesting, right? And so let's let me show all that to you somewhere. Where do I want to put that in code? Let's do that back in the pointers file. All right, so here's that one. I'll section it off. New thought. All right, so there's that. And now let's do, all right, we already have X and P, right? We've got X, and we've got P pointing to X. We're holding 6 now because we did that. But what can we do now? Let's set this up. So we already got P and X correctly. Let's make Q, right? Q also needs to hold the address of X. And Q equals the address of X. That'll work. Or, right, because P is already holding the address of X, you could have said int star Q equals P. Because just P by itself holds that address. It's just a box holding that. So, or you could have done equals just P. That would work. Let's do the others. I've got int star star R holds the address of Q, right? Holding the address of Q. And then, just for fun, we'll do the Z. Int star 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 Z equals the address of R. Like the second you add an ampersand, it's going to add a star. Okay? This is a pointer to that thing. Because if R is an int star star, we want to hold its address, we need to put it in an int star star star. But now we can get to all the values. We can get to X in all the ways that we just said, right? And set it or print them. So we can see out just X by itself. We can see out star P, because P is pointing to X. We can do star Q, because Q is pointing to X. We can do star star R, because R points to Q, another star will bring it to X. And then we can do triple star on, I'm sorry, did I call this X again? I meant to mean like Z. Sorry. Can't have X twice. There. That's what I want. And so it'll be triple star Z. Because one star gets you to R, a second star gets you to Q, a third star gets you to X. So that's actually an easy way to remember how many stars you need if you have the diagram in front of you. every star follows an arrow. See that? 1, 2, 3. Okay. That's the goal. All right. Any questions about any of that? All right. So, if we are good, let's talk about new errors that you could have. All right? Because the second you have pointers, there's a whole new class of issues that can happen in your program. The second you're talking about memory. Because maybe you're holding an address that you maybe shouldn't hold, like a garbage one, or you hold that special 0 null address that you're not allowed to use. So let's talk about seg faults. All right? So there are many programs running on all the computers, right? Including the class server. There's a million programs being run on my computer, right? And on the class server. So each program doesn't get all of the RAM. They're all sharing it together. Okay, so your program's only getting a little bit of memory assigned to it. It only has it has some range of addresses that belong to it, but no others. Maybe those are part of like PowerPoint or Firefox. Okay. So if you try to go to a memory address, you try to like somehow shove it into a pointer, and you try to dereference that pointer, or even null, right, which you also don't get, you get a special kind of error called a segmentation fault. Like seg fault for short, that's all I'll call it. But it's meant to mean like that address was not part of your program's segment of memory that was assigned to it. That's kind of how you can think of it. It's definitely a runtime error. You cannot really recover from that. It's like you thought that address was yours and you could get it, but no, you can't. Okay, so that's going to be the goal there, seg fault. So let me show that to you. Dun, dun, dun. Seg fault.cpp. Let's talk about that. So like the easiest way to get a seg fault is like have p point to nothing. Hold the null address. So that's the 0 address that nobody ever gets access to. We're all agreeing that we're never going to use it. If you try, it's going to be a runtime error. It's called a segmentation fault, or a seg fault for short. And then this is what you see. You may have seen this already when you were using arrays. Have any of you seen this already? Got that error before? So secretly in arrays, it's doing pointer stuff. I'll show you that later one day. But it was trying to go, like you're trying to go past the end of an array, and that was part of memory. That was a memory address that was not yours again. So same idea. Good. All right. So yeah, I just have a few more examples. Are we still happy enough? I know this is a lot of new information. It's important to study this stuff. But if we're good, I have a couple more examples. All right. So I've kind of showed you that pointers are mostly equivalent to references right now. There's some other powerful things that they can do that we'll get into later. But let's kind of talk about their differences. All right, so let's do a swapping example with references and then pointers. Right, because we know that if we want to touch somebody else's memory, like actually do a swap or like an increment or something, we have to use either references or pointers. So I'll call this file swap by ref and by pointer. All right. So let's say I have an int x equals 42 and an int y equals 43. I'd like to swap them using a function call. All right. So I can make a swap by reference that passes x and y by reference, and hopefully it should swap them correctly. So let me prove that to you. We'll do that one. This is one that we kind of understand already. So swap by ref. It's going to be a void function that takes two things. They can be called something different. Let's call them A and B. And they're going to be taken by reference. Right? Int reference A, int reference B. And that's going to allow us to touch main's memory, because x and y are going to be passed into reference values, and now they're suddenly accessible. It's like main stuff. They're not being copied. Okay? So how do we swap things? Well, you make a temp variable, set it to 1, A equals the other, and then B equals temp. And so that'll work. That's nothing new, but that's one option, right? So we get 43, 42. They did swap correctly in main. And yeah, any questions before I draw a picture of that, just to remind us why it works? All right. So let's talk about it. Main had two variables. It had an x and a y. They were 42 and 43. All right, and then we called from main swap by ref on x and y. And I'm going to draw everything that swap by ref owns in green for the same reason that I did it before. So I'll just call this swap ref to save my wrist. But swap ref had an A and a B, and we were setting the int reference A to x, because that's what we passed, and we were setting the int reference B to y, because that's also what we passed. Okay, so we're doing that, and that means because they're references, they're not in any new memory. We think of it that way, at least. And so A, as far as swap ref is concerned, is this box. B is that box. So all the green things swap ref knows about, and so it's understanding that that's part of main. All right, somebody else's memory, and then it's going to make temp equal to A. Temp is its own local variable. Temp equal to A, 42. A equal to B, 43 goes there, and then 40, and then B equals temp. B is the same box, so that's why that becomes 42. And then once this returns, we actually did the change, right? Is that coming back to us? Make enough sense? So that's one way to do it. And then let's do it using pointers, because this is secretly what the references are doing for you anyway. So, how do we want to call this? Let's make it swap by pointer, I guess. And I need to pass, I'll change this in a second. It's got to be the addresses. And hopefully they'll get changed. So swap by ref looks like that. Swap by pointer will look like this. I'm going to get the addresses of ints. And that's going to be a way I can mess with them. All right? And it's going to be temp equals dereference the pointer to get the actual int. Dereference those, change them, star b equals temp. Temp is still a normal int. It's still just a temporary value. It doesn't have to be a pointer. It's fine. But that is going to be that answer. And now when I call it, let me split screen. Now when I call it, I got to give it the address of x and the address of y, because the types have to check out. Right? So that's going to go into A, and the address of y is going to go into B. All right? And so we're going to see them swap back to 42, 43. It will work. Isn't that glorious? That's what references are secretly doing for you. Any questions before I draw a diagram on this one? All right. So yeah, let's talk about what's going on in memory. So main, let's go back to blue. What was main doing? So we actually swapped things. So main had two local variables. It had x and y, and they were 43 and 42 because they did get swapped. And then we call swap by pointer on the address of x and the address of y. So we called swap by pointer. I'll just say swap pointer here. And what that had were no references. It had pointer variables. And those are local variables still. Those are normal variables. Pointers are still just normal variables. It's just what they hold is special. So A and B, those were part of swap pointer. Those were local variables to swap pointer. They were pointers, though, holding the addresses. And so let's say that x lived at address 100 and y lived at address 104 for fun. When we call it like this, we're saying, all right, A becomes, in star A becomes the address of x. So A holds 100. And then we said, in star B, that will become the address of y. So that's, in this example, 104. And so now I have this pointer relationship going on just like that. You see it? That is going to make all the difference there. And so, yeah, to do the swapping this way, we'll make a brand new temp variable. Temp becomes star A. So here's temp, just a normal int. Temp becomes star A, which is 43. Follow the pointer. And then we say star A equals star B. So star A is about to change. We're going to change this box with the value of star B. So we're going to place 42 right into there. All right. So that's what we're going to do. So now that becomes 42 because of that. And then finally, star B equals temp. So star B is this box. Set it equal to temp. So become 43, please. And that is how, and then this returns, and it did the work, though. That's how you indirectly access the x and y, by passing those addresses. Okay? Any questions about that? Because that's kind of the last piece of the puzzle there. Yeah? These are stack diagrams, yes. That's exactly right. Talking about who owns which memory, which function. Good. All right. So if we are good, I have one last thing to show you for the day, not to make your brain explode too much. There's plenty more to talk about, but I want to talk to you about having pointers to like normal types, different types. Like I was giving you a bunch of int pointers today. You can have a pointer to anything. Pointer to a double, pointer to a bool even if you really wanted to. Let's make a pointer to a string. That's totally fine. You can make a string s. Somehow looks like this in memory, right? Somehow holds A, B, C, D. And everything has a starting address. So like S has a starting address. Let's say it's 100, right? You can make a string star. You can make a pointer to a string, have it hold that address. So SP is essentially going to be a box holding 100 and pointing to S. You see that? And now, if you want to do string stuff through SP, you have to be careful, right? Because what is SP? It's just a box that's holding a big number. It is not the string. Okay, so this won't work at all. SP.size makes no sense because SP is like the number 100. You can't do 100.size. That does not work. You have to get to that string still. You have to follow the pointer, right? So this is something you can do. Do star SP. The star SP follows it and gets you here. And then that has a dot size operation. That's fine. That'll work. And the parentheses are unfortunately necessary because of precedence rules. And so everybody is like, I want this ability. Like this is necessary for me to have pointers to classes like this, pointers to objects. And I want to call member functions on them. But I hate this syntax because that's a lot of shifts, right? We don't like these parentheses. No fun. So everybody decided that we're going to make a brand new operator called the arrow operator to do both the dereference and the dot all at once. All right, it's like this. It's a dash and then a greater than sign. It's meant to mean an arrow. Okay, that's what it's going to do. So both of these lines, they're equivalent to one another. Okay, so star SP, that will get you to S, and then you can do the dot on it, which makes sense because it's a string now. But most people prefer SP arrow size. Okay, and if you had a member variable like SP arrow X, go inside of it. Okay, but yeah, just remember that pointers are just big numbers. You can't do a dot on them. You're not ready. You have to get to the thing you're actually pointing to. Get to the actual object that that thing is pointing to. Right? So it's called the arrow operator. Dun, dun, dun. Right, so let's include the string library and do exactly that. So I have a string s equals something, and then I can make a string star, string pointer SP, have it hold the address of s, and yeah, now I can get to the string through SP. So again, I can't do this. SP.size won't work because SP is just a big fat number. It's not even going to compile. 64 bits are very large. So it's going to say something along those lines. Request for member size in SP, but it's a pointer type. Maybe you meant to use the arrow? Well, that's nice of it. All right, yeah, so it's just like, this won't work. Won't work. SP is just a number. But you can follow that number to the string, all right, using either the dereference and the dot or the arrow operator. So see out, like to spell it out, star SP gets you to S, right? And then you can do string stuff. Give me the size now, please, all right? So that will work, or equivalently, everybody decided this was too much typing, so they said instead, SP, arrow size. Both of those mean the same thing, right? And so they're both going to print 4 because that's the size of the string, all right? So yeah, one day you might want to have a pointer to an object and do some of the operations on that object through the pointer. Now you know how, right? So yeah, any questions about that or anything else? Because I think that's where I want to pause for the day. Again, yeah, this is definitely something to study. This is a harder topic, but it's going to help us understand what's going on under the hood. And I think we've already learned a little bit, so that's wonderful. All right, so that's just going to be the lecture for the day because you have a lab. That is a 2-week lab, and so yeah, the rest of the time is all yours to work and ask good questions.